So our goals are to find our local maxes or our local mins, and the way we do this is by coming up with an equation, then taking the first derivative and setting it equal to 0, which will give me those critical values which tell me where my function is maximized or minimized. So again, the goal is to maximize or minimize to find your local max or local mins. So you're going to go in here, you're going to read your question very carefully. You're going to kind of draw a picture, label some variables, write your equation. Whatever it is you're maximizing, if you're maximizing volume, you need an equation for volume. If you're maximizing surface area, you need an equation for surface area. But maximizing or minimizing, whatever it is, you create that equation. And once you've created that equation, you come up with your critical points using the first derivative, and then determine if you're talking about a max or a min at that critical point to answer the question. So that's what optimization is all about. So they're going to give you a question such as this one. An open top box is to be made by cutting small congruent squares from the corner of a 12-inch by 12-inch sheet of tin and bending up the sides. How large should the squares cut from the corners be to make the box hold as much as possible? So you're going to have a square piece of tin, and you're going to turn it into a box. And the way you're going to turn it into a box is by cutting corners out of it. And when you do, you'll fold up these sides. You'll fold them up, and it will create an opened box, a box with an open top. So when you create, then when you have it, I don't even know if I can do this in 3 dimensions, people. So when you fold it all up, you'll have a box looking something like this. Okay, so when you've cut those corners out and you fold it up and you solder or whatever the corners together, then you will have a box. So an open top box is made by cutting out these corners and folding this thing up. How large should the squares be in order to make the box hold as much possible? How much the box will hold is the volume. So you're going to maximize the volume. You want the maximum volume inside the box that you're creating. So you want to maximize the volume. So the goal is to write an equation for volume and then use your calculus to maximize that volume. So if we have a box that is a 12 by 12, and we're going to cut corners out of it, and these are square corners. So suppose these are x by x corners that we're cutting out of each corner. These are perfect squares that we're cutting out of each corner. So when we do that, this is going to be a length that we're looking for, and this is a length that we're looking for. Now you know the volume is length times width times height of a box, a rectangular cube. So now, this region here, if the whole thing is 12, then this region that I've selected, this right here, what is its length going to be? There you go, 12 minus 2x. Here's your other region right here. If the whole thing is 12, what is this small length right here? Also 12 minus 2x. So your box has a length of 12 minus 2x, a width of 12 minus 2x, and what's the height of this thing going to be when you fold it up? There you go, the height is x. This part right here is x. So you have a 12 minus 2x, a 12 minus 2x, and a height of 12. So there's your volume. Yeah, a height of x, I'm sorry. Okay, so let's go ahead and figure this out. So let's multiply this out. 12 minus 2x times 12 minus 2x. 12 times 12 is 144. Your outside and your inside is a negative 24, so that's a negative 48x. And you're going to get a negative or a positive 4x squared, all times x. So that's when you do FOIL in the first two binomials. And then when you multiply this times x, you have 144x minus 48x squared plus 4x cubed. This represents the volume of the box that you've created when you cut those squares out of the corners and fold it up. Now, if you want to maximize the volume, you're going to take the first derivative of it and set it equal to 0, because that's telling you where you have horizontal tangent lines at your local maxes and local mins. So I'm going to take the first derivative, which is dv dx, or v prime. The first derivative is 144 minus 96x plus 12x squared. That is my first derivative of my function. Now again, that tells you the slope of the tangent line. And at a max and min, the slope of your tangent line better equal 0. So we're going to set the first derivative equal to 0 in order to find the critical points, which are hopefully going to give me the locations of the local max or the local min. Now to solve this equal to 0, I need to factor it. And I think I'm missing, no I'm not, that's supposed to be an x there. I can't do it backwards like that. I need to reorder this. I'm going to make it a 12x squared minus 96x plus 144. I need to reorder it. Now to factor this thing, I'm going to start by taking a GCF of 12 out, leaving behind an x squared minus 8x plus 12. Then I'm hoping that thing will factor. If it doesn't, I'd have to go to the quadratic formula. Let's see, an x and what multiplies to be 12 and adds to be a negative 8, negative 6 and a negative 2. So this is working out very nicely. So then I set each of these factors equal to 0 to get my critical values of 6 and 2. Now, I don't know if both of these are maxes or both of these are mins or what they are, so I have to create a sign chart to determine if these are maxes or mins. So I go and I create a sign chart where I put my 2 and my 6 in my sign chart. Okay, my factors are x minus 6 and x minus 2, and my first derivative is the product of 12 times the x minus 6 times the x minus 2. And I want to know the sign of the first derivative. So if I pick a test point to the left of 2, suppose I pick 0, then 0 minus 6 would be a negative 6, which is a negative value. 0 minus 2 would be negative 2, which is a negative, and their product would be positive. Then if I pick a number between 2 and 6, suppose I pick 4. 4 minus 6 is a negative 2, which is a negative. 4 minus 2 is a positive 2, which is a positive, and their product would be negative. Then if I pick a test point to the right of 6, say 10, then 10 minus 6 is a positive 4, which is positive. 10 minus 2 is a positive 8, which is positive, and their product is positive. So the first derivative is positive between 0 and, or negative infinity and 2, and between 6 and infinity, and it's negative between 2 and 6. So this means I'm increasing, then I'm decreasing, and then I'm increasing again. So my function is increasing, then decreasing, then increasing again. My original function is increasing, decreasing, and increasing again. So if I'm going from increasing to decreasing, here at 2, I should have a local max. If I'm going from decreasing to increasing at 6, I should have a local min. Now the question said maximize the volume. So we're looking for the max, and the max is occurring at a value of 2. So it looks to me like we should be maximizing this function at an x value of 2. And the question said, how large should the squares cut from the corners be to make the box hold as much as possible? And if that is my max, up here, this x value is that little amount we cut out of the corners. So that means that that little square, how large should the square be? The little square should be a 2 by 2. All right. Now, if that feels a little uncertain, we can check it because we have such nice, powerful calculators. we can take our volume function, which was 144x minus 48x squared plus 4x cubed, graph this thing and see if it really does max out at an x value of 2. See if the volume is truly a maximum at an x value of 2. So if we go to our calculator, we can kind of double check our work here. What's taking it so long? Come on, little calculator. I really don't want to have to restart this thing. So there it is. Okay. So we said our volume was 144. 144. What's sluggish? X minus 48x squared plus 4x cubed. Okay, and I'm gonna, God, do a zoom fit on this thing? See if it'll take a zoom fit. Oh, this thing is so slow. Oh, that didn't work. Did anybody get a graph out of zoom fit? Okay, change it. I'm going to do a zoom. I'm going to make it a small screen, and then I'll play with it. Do a zoom standard. Did it graph anything? It's okay. It's blinking. Okay, let me go to my window. All right, I'm going to probably have some pretty big numbers here. If I have 144x, I got a maximum of 2. Let's go up to y max. I don't know. Let's multiply this times 100. Okay, now we're doing a little bit better. This is a cubic function, so it should have a down behavior on the left and an up behavior on the right. So I could get a little more x values if I wanted them. Multiply this maybe times 10. Okay, there it is. I got a little extreme. But you can see your functions going up and back down and then back up. So it does have a max here where my x value is 2 and a min over here where my x value is 6. Now if you get beyond 6, say if you let x be 10 or 15, think about the box. The box was only 12 by 12. So your x cannot be that big. If you're going to cut 12 inches out of it, then you don't have a box. Right? Right. Or if you cut 6, you can't have a box because the 6 and the 6 takes up the whole box. So really your domain of your box to cut x out, that didn't work. Yeah, it did. If your box is a 12 by 12, your x can be cut like 0, which really wouldn't work either, but you cut 1 or 2 or 3 or 4. But your x can't get any bigger than 6 if you're cutting it out of both corners and the thing is only 12 inches wide. So between 0 and 6, we definitely have a max occurring in an x value of 2. So you maximize the volume of the box by taking out 2-inch squares out of the corners of that little piece of tin to get that maximum value. So really, this algebra is not that difficult, but this is a pretty intricate situation where if you have cardboard boxes or whatever, or tin boxes that you're having to create for some company, you've nailed what's the maximum way to do this, what's going to make the biggest box by using just the simple algebra we just used to come up with those values. So it's a really good application. Really good application. Okay, so let's take a look at the next one. You have been asked to design a 1-liter can shaped like a right circular cylinder. What dimensions will use the least amount of material? And when you do your homework, they'll give you images that will kind of show you what you're designing here so it's not so blank. So you're going to have a can, a cylindrical can, Okay, a cylindrical can, and it says you've been asked to design a 1-liter can. What dimensions will use the least amount of material to create the can? Well, the material to create the can is the surface area. Okay, right. The surface area of the can is what you're trying to minimize. So, if you think about a can is a rectangular piece of tin or aluminum, right, that you roll up to form the cylinder, okay, right? And then you have a top that you're going to have to put on it and a bottom that you have to put on it. So you have a rectangle and you have a top, which is a circle, and you have a bottom, which is a circle, and that's all your surface area. So your surface area is the rectangle and the circle and the circle. Well, how are we going to do this? Okay. The area of your circle is pi r squared, right? There's your top and your bottom. And I've done this so many times that this comes very naturally to me. This length, let's see if I can explain it now. This length, is 2 pi r, because it's the same thing as the circumference of the circle, right? This length of this side of this rectangle is the circumference of the top and bottom of the can, which is 2 pi r. Okay, it's the circumference of the circle on the top and the bottom. And then this would just be considered the height of the can. The height of the can. So the surface area, which we usually indicate by SA, is the area of the rectangle, which is 2 pi r times h, plus the pi r squared plus the pi r squared. So there you go, 2 pi r h plus 2 pi r squared. That is the surface area of a right circular cylinder. Now, did they give us anything that we can use? You have been asked, there you go, that you've been asked to design a 1-liter can. So you got 1,000 cubic centimeters. That's not surface area. What is that? That's right. You're given that the volume is 1,000 cubic centimeters. Well, what is the volume of a circular cylinder? You might remember it's the area of the top times the height of the can, right? It's kind of like taking... No, that's surface area. It's the area of the top of the can, which is pi r squared. And then if you slide the lid, it's kind of like if you could leave a pad. Okay, if you take the top and slide it to the bottom, that's your height. It's 2 pi r squared times height is the volume of a right circular cylinder. So we know that this is 1,000. So now we've used our given, and we know that this is the formula we're supposed to be minimizing. Okay, this is the equation we're supposed to be minimizing. Now this equation that we're supposed to be minimizing here has 2 variables in it. It has r and it has h. We need to get rid of one of them. I suggest we get rid of h. Well, the way to get rid of h is to take this information and solve it for h. So if I solve this for h is 1,000 divided by pi r squared, and take this and plug it into your surface area equation, so you get everything in the variable r. And there is your surface area equation in one variable, the variable r. So now you have this ugly thing. You're going to want to minimize it, which means you've got to take the first derivative of that thing and set it equal to 0. Okay, that's your goal. Well, this looks terrible. Let's see if we can clean it up a little bit. Okay, 2 times 1,000 is 2,000, and the pi's are going to cancel, and the r's are going to cancel, leaving you an r, right? And then remember, what are you going to do to this thing? You're going to take the first derivative of it. So if I've got to take the first derivative of this thing, I'm going to write this as 2,000 r to the negative 1. All right, remember your goal is to get into one variable, and the one variable here is R. And in the question, I didn't know, I had no clue that 1 liter was 1,000 cubic centimeters. This was given in the question, okay? You're not expected to know that. It was given. Okay, so we have an equation. We're tickled that we have an equation. Now we've got to figure out how in the world to take the first derivative of it. All right, so here we go. How am I going to write this? First derivative. Like A. We'll leave it like A. Okay. We'll just call it A. Surface area is A. Okay, so this is going to be negative 2,000 r to the negative 2 plus 4 pi r. There's our first derivative. We got to set this thing now equal to 0. Set it equal to 0 to find your critical values, to find either a local max or a local min, and we want the min. Okay, to set this thing equal to 0, this is not pretty. Okay, I need to be able to factor it somehow. I've got to combine these terms. So let this be a negative 2,000 over r squared again. And if I get a common denominator of r squared, this would be a negative 2,000 plus 4 pi r cubed, right? So I need to combine it into one fraction. Once I get it into one fraction and I want to set it equal to 0, then I really just set the numerator equal to 0. Because if the numerator of the fraction equals 0, then the fraction equals 0. Yep, 4 pi r cubed equals 2,000. You're trying to solve this thing for r. R is your variable. 2,000 divided by 4 is 500, right? So R, this is my critical value, okay, that's got to go in a sign chart, okay, is the cube root of 500 over pi. Boy, I'm low on this page. I'm writing too big. Okay. Now then, I've done an approximation on this. This is approximately 5.42. So let me see if I can fit a sign chart on here. Okay, my critical value is 5.42. And my first derivative, oh lovely. Okay, my first derivative, get back on the screen. I'm going to use this one. This is the best one, I think, of everything up there. Is a negative 2,000 plus 4 pi r cubed over r squared. And what I did was I picked up my calculator and I put numbers into the calculator to determine if it was going to be positive or negative. I put a 1 in and I put a 10 in. When I put a 1 in for r, I got a negative 2,000 plus 4 pi, which was definitely a negative value. When I put a 10 in for r, I got a negative 2,000 plus 4,000 pi, which is definitely positive. So that means that my original function, my area, okay, my first derivative of my area was negative, which means my area is decreasing. Then it's increasing. So if it's going down and then up, is this a local min or a local max? A local min. So a local min at r equaling approximately 5.42. Okay. Yeah, but I'm going to have to move up this page somehow, because I am on the bottom corner of this page big time. Okay, so I'm going to come up here somewhere. What was the question? What are the dimensions of the can? Let me get up here where I have a little more room. What are the dimensions of the can? Somebody's opening a can out there. I just heard you. Okay, what are the dimensions of the can that minimizes the surface area. Okay, the radius of the can needs to be about 5.42. So the dimensions of the can, what do they want? The height? Let's give them the height. We just gave you the radius, people. Okay, the height of the can needs to be 1,000 over pi r squared, which will be 1,000 over pi times 5.42 squared, which I believe turned out to be about a 10.84. And all of this is in centimeters. We give them the radius and we give them the height, and they better be able to figure out how to make the can from there. Again, this was not difficult, and you really solved an interesting task. Okay, think about the millions of aluminum cans they make for all the Coke that we buy, right? And they want them cylinders because they hold better in your hand when they're cylinders. When they're square, they're a little harder to hold. They're comfortable in your hand when they're a cylinder. They're a pain to pack. Okay, they don't fit well anywhere when they're cylinders, but they're comfortable in your hand, and we've come up with the way to minimize the amount of aluminum necessary to create that can that'll hold a liter of liquid for them to produce. That's a very interesting piece of knowledge, right? I mean, that's kind of cool that with the little bit of calculus that we've learned, that you can come up with figures like this. Pretty fun. You're all looking like you're totally bored out there, like, well, whatever. Who really cares? Let's just finish this. Okay, here's another one. Straight from the textbook, I pulled this. And this one has some nasty algebra in it, but it's an interesting question. And it says, a right triangle whose hypotenuse is the square root of 3 is revolved about one of its legs to generate a right circular cone. Okay, we're going to have a right triangle. Let's see if I can sketch this lovely little image.
That's x square root 2. That's a 30, 60, 90. That's the square root.
Well, I just took it straight from the book, so whatever. Okay, so here's the image. You aren't paying attention to me anymore. Trying to draw this sketch, which is not easy for me to do. Okay, this hypotenuse here is the square root of 3. And we're going to spin this thing around. Let's see if I can do this. And I'm doing it in a pen, no less. That is not fun. Okay, this thing is spinning, and as it spins, can you visualize? It's not supposed to look like a pyramid, okay? It's a cone. When it spins, it creates a cone. Hey, now that's pretty good. I did that quite nicely. Even in my pen. Okay, so there it goes. Find the radius and height and volume of the cone of the greatest volume that can be made this way. Okay, we'll maximize volume. The question wants me to maximize the volume of the cone. That's the question. So in other words, we need an equation for the volume of that cone, and then we need to maximize it. Okay, what is the volume of a cone? It's a third of a cylinder. Right. It's the third of a cylinder. There you go. Okay, it's a third of a right circular cylinder. Okay, it's the third of a circular cylinder. That's the volume of a cone. So we need to maximize that. Well, we have too many variables. We got an R and an H. We need to get rid of something. Let's see if we can get rid of H. Okay, if this here, how did I do this? If this is, okay. Let the height be H, of course, right here. And this would be R right here, your radius right there. Okay, and this was a right triangle. So therefore, we know that r squared plus h squared equals the square root of 3 squared. Well, that is cubic. Okay, so r squared plus h squared is 3. Solve this thing for h. H squared is 3 minus r squared. H equals the square root of 3 minus r squared. So take this, knock the h out. Oh, I didn't mean to go right through my word, but I sure did. Okay. And so this volume of this circular cone, this cone, is going to be 1/3 pi r squared times the square root of 3 minus r squared. It's not very pretty. There it is. So we need to maximize the volume, which means we take the first derivative of that thing, set it equal to 0, find your critical points, create a sign chart, find the local max. That'll tell you the radius that will give you the largest cone, or it will give you the volume of the largest volume for the cone. Oh boy. Okay, so if we've got to take the first derivative of this thing, this is 1/3 pi r squared times 3 minus r squared to the 1/2 power. Oh my, this was ugly. Oh my. This took me a while to do. Okay, so here we go. The volume is going to be, I let this be, it's a product. So I let this be my first and let this be my second piece of my product. So if I'm going to do the first times the derivative of the second plus the second times the derivative of the first, it's 1/3 pi r squared, that's the first, and the derivative of the second is the chain rule. It's 1/2 times 3 minus r squared to the 1/2 minus 1 times a negative 2r. That's the first times the derivative of the second. Plus the second which is 3 minus r squared to the 1/2 power times the derivative of the first, which is 2/3 pi r. And this is your plus sign right here. Okay, so the 1/2 and the negative 2 knock each other out. So this, I hate to do it with this pen. What are you going to get? You're going to get a negative 1/3, right? And the 2's cancel. Your r times your r is r cubed. Right? Times 3 minus r squared to the negative 1/2. And over here you have 2/3 pi r times the square root of 3 minus r squared. Okay, a little bit further. This is a negative 1 pi r cubed over 3 times the square root of 3 minus r squared. We need a common denominator. Okay, the common denominator is 3 times the square root of 3 minus r squared. So you're not changing the first fraction, but the second fraction is going to become 2 pi r times 3 minus r squared. So this becomes a negative pi r cubed plus a 6 pi r minus a 2 pi r cubed over 3 times the square root of 3 minus r squared. Are we having fun? Doing this in pen is always interesting for me. I hate to do this kind of stuff in pen, but my pencil just does not take well with this camera. So this is a negative 3 pi r cubed plus a 6 pi r all over 3 times the square root of 3 minus r squared. That, my friends, is the first derivative, right? That's dv dr, or v prime. Now, once you get the first derivative, to either maximize or minimize, you set the thing equal to 0 to find your critical values. So when I set this equal to 0, I really only want to set the numerator equal to 0. And so to set the numerator equal to 0, it becomes a negative 3 pi r cubed plus 6 pi r equal to 0. Factor out a negative 3 pi r, and you get r squared minus 2. Now you got some things happening here. You get the negative 3 pi r equal to 0, and the r squared minus 2 equal to 0. So you get r equaling 0, or r equals a positive square root of 2, or r equals a negative square root of 2. Now, remember what we're talking about now. We've been doing so much algebra here, we've got to back up a minute and think, what in the world's going on? This is a cone, and r is the radius of the base of the cone, right? So is r equaling 0 a good idea? No. Is r equaling a negative square root of 2 a good idea? No, okay. They don't fit the real world situation. So the only one here that's of any major worth to us is this one. And we hope that value actually maximizes the volume function. So we'll check it. Okay. Now, be really careful when you pick your test points, because you've got to be to the right of 0, right? 0 is over here, and negative square root of 2 is over here, but the only one we're interested in is the square root of 2. So you pick a test point, it's got to be greater than 0. So something bigger than 0 and less than the square root of 2, you could pick 1. Okay, and how did I do this? I think I just actually did the whole thing. No, I didn't. I did the whole thing here. What did I do? I took a negative 3 pi r, and then I did the r squared minus 2. And don't forget you have a denominator of 3 times the square root of 3 minus r squared. Here's all the pieces of the sign chart. Okay, and when you do this, if you pick a number like 1, a negative 3 pi times 1 is negative, 1 squared minus 2 is negative, and 3 times the square root of 3 minus 1 is positive. So a negative times a negative over a positive makes it positive here. If you pick a number to the right of the square root of 2, and I think I picked 1.5, okay, then a negative 3 times 1.5 is negative. A 1.5 squared minus 2 was positive, and a 3 times the square root of 3 minus 1.5 squared was positive, which gave a negative result. So that means we are increasing and then we are decreasing, which makes the square root of 2 a local max. So we did maximize the function at an r value of a square root of 2. so then you got to read the question again. The question was, that's enough to make y'all dizzy. Find the radius, height, and volume of the cone. Well, the radius needs to be square root of 2. The height needs to be 3 minus the square root of 2 squared, which is square root of 3 minus 2, which equals 1. And then the volume would be 1/3 pi r squared times height, which is 1/3 pi square root of 2 squared times 1, which is 2 pi thirds, which is approximately 2.09 units cubed. It didn't tell us what units we were in, so we'll just say cubic units. There's your answers. Okay, so the worst part of that was algebra. Yes?
On the sign chart, choose like 2, for example.
If your radius is 2, does that get you out of the domain?
Yeah.
Do you go too far? Yeah, that gets you too far out there.
Yeah, that's why.
No. That's why you got to kind of keep them close to you, because you got so many critical values so close together there. Okay, be careful you don't get outside your domain. Well, I can't believe I got all of that on one page. Tiny writing. Okay, but there it all is. Okay, let's play with the next one. Except for you're all needing to take a break, aren't you? You're all starting to wander about. How about I pause the recording and let y'all take a quick break? If I can find the recording.
You just recorded us talking about kissing Brad Paisley.
Well, I had to figure out how to audit that thing, huh? Okay. It said it was paused, and when I hit pause, it changed again, didn't it? Okay, where is my... Here it is. Okay. Okay, so here we go. Let's do another example. Okay, this is the last example of this section that we're going to do. We're not going to do the revenue one, because after I got in there to do homework for you guys, they don't even have any for you. So we're not going to do that. So let's talk about the rectangle being inscribed in a semicircle of radius 2. What is the largest area the rectangle can have, and what are the dimensions? So if you have a semicircle, I don't do this very well either. I'm not very artistic, people. Okay, here's your semicircle, right there, and it has a radius of 2. And we're going to put a rectangle inside here. Like so. Okay, so there's your rectangle inside your semicircle. And what do we want to do? Find the largest area the rectangle can have. Well, let's go ahead and put a y-axis in. Okay, so the area of the rectangle is length times width. That's no major rocket science, right? So what is the length and what is the width of this rectangle? Well, this point here, let's call this point xy. If we can figure out that ordered pair, we can tell you the height of the rectangle and then double the x for the width of it. So now we got to figure out what are these values going to be. How are we going to come up with y? Well, if you have a circle whose radius is 2, what is the equation of the circle?
1/2.
No. What is the equation of the circle? It's x squared plus y squared equals r squared, right? So if I solve this for y, I'll get y squared equaling 4 minus x squared, or y equaling the square root of 4 minus x squared. So this ordered pair becomes x square root of 4 minus x squared, because the radius of the circle is 2. So now if I want to get length times width as the area of the rectangle, if the longer side is my length, what is my length? If the horizontal side is the length is 2x, right? And the width is like the height, which is the square root of 4 minus x squared. This is a dot for multiplication. So there is your area of your rectangle inscribed inside a semicircle of radius 2. So now, if we're going to get the largest area, we want to maximize the area. Then I'm going to take the first derivative of area, set it equal to 0, get the critical value, see if that is a local max, and then we're good. So before I take the first derivative, I'm going to go ahead and write this with a 1/2 exponent instead of as a radical. And this will be the product rule, first times second. So the first derivative, dA dx, which is the first derivative of area, will be the first, which is 2x, times the derivative of the second, which will be 1/2, times 4 minus x to the 1/2 minus 1, times negative 1 by the chain rule. Plus the second, which is 4 minus x to the 1/2, times the derivative of the first, which is 2. Okay, so the derivative is looking pretty complex. To play with this for a minute, let's clean it up a little bit. Well, 2x times 1/2 gets rid of the 2, and you got the negative. So this is what, a negative x over the square root of 4 minus x. Am I missing a sign here? 4 minus x squared. Yeah, x squared plus 2 times the square root of 4 minus x squared. Hold on a second. Because this is x squared, right, there you go. So the derivative in here is now going to be a negative 2x. There we go, because I wrote that incorrectly, and that's supposed to be... So this ends up being 2x, negative 2x squared, right? There we go. Now, if I'm going to set this thing equal to 0, I need a common denominator of the square root of 4 minus x squared. So this is going to be a negative 2x squared plus 2 times 4 minus x squared. Which equals a negative 2x squared plus 8 minus 2x squared over the square root of 4 minus x squared, which is a negative 4x squared plus 8 over the square root of 4 minus x squared. There is the value of my first derivative of area, which we are trying to maximize. So to maximize this, I set it equal to 0, find my critical values, and create a sign chart. Well, for a fraction to equal 0, the numerator of the fraction must equal 0. So a negative 4x squared will equal a negative 8, or x squared will equal 2, or x will equal plus minus the square root of 2. But x is a distance. It's like half the length of my rectangle. So I cannot have the negative version. I can only have the positive version for it to apply to this application. So then I come in here and create a sign chart. But once again, be very careful with the size of the numbers you use, because you can't get it, because you really have more than one critical value. You still got the negative square root of 2 over here also. So you got to be careful that you don't pick too big or too small of numbers. So if your radius is 2, how big can x be? X cannot be any bigger than 2. Okay, so x has to stay smaller than 2, bigger than a negative square root of 2 in here. So we have our this is what we're setting equal to 0. So we have a negative 4x squared plus 8. We have a denominator of 4 minus x squared. So our area is going to be the top over the bottom. Our first derivative is going to be to get the sign of the top over the bottom. So if I pick a 0 as a test point, this will be positive and this will be positive, and a positive over a positive makes a positive. If I pick, and I'm staying with a pretty small number, I'm going to pick, huh? Yeah, because 0 is not a critical number. A radius of 0. No, it could not. Well, let it be 1.5 then. Oh, would that be right? Would 1.5 be less than? No. 1. Okay. If we do 1, then it'd be positive and positive and positive. And over here, if we let this be, and I just chose 1.5, because the square root of 2 is what? What is the square root of 2? Is it 1 point what? Okay, so I can pick a 1.5. Okay, and when I put a 1.5 in here, I ended up with a negative. It took me, I had to actually put all that stuff in the calculator to get that result. Okay, so now your first derivative is positive, which means your area function is increasing and then your area is decreasing. First derivative being positive means your area function is increasing. Negative means it's decreasing. So if you're going up and then down, sure enough, this is a local max. And this is an x value. Okay, so now going back up to my image up here, then to maximize this, to maximize the area of the rectangle, then we need x to equal a positive square root of 2. So the dimensions of the rectangle, what are the dimensions going to be? This is x and this is x. So your dimensions are, well, if that's x, let me get, well, there's a lot we need to do here. Here's your box. This is 2 times the square root of 2, right? And the y value is the square root of 4 minus the square root of 2 squared, which is 4 minus 2, which is the square root of 2. And those are the dimensions of the largest rectangle that would stay inscribed in a semicircle of radius 2. Pretty cool. So the answer would be, I guess, 2 square root of 2 times square root of 2 would be your dimensions. Okay? Because in your image up here, this is a square root of 2 plus square root of 2 plus square root of 2 is 2 square root of 2. Square root of 2 plus square root of 2 is 2 square root of 2. Isn't that a mouthful? Okay, and now that my recording is extremely long, because it evidently recorded our break, even though I thought I paused it, that is the end of that section.